In the previous video, we looked at Ptolemy's contributions to understanding the sort of the motion of the planets in the solar system, and it got pretty complicated. So I'm just going to reiterate the different steps that he used. He made epicycles, which orbit around deferents, which go around the Earth. That's the fundamental ideas of the plan. You just keep adding circles. Now it's important to understand, well, why would you do this? Why would you keep adding circles? Why wouldn't you try to make one continuous orbit that fits, regardless of the shape of it? And the reason is because the Greeks really liked the circles. There was the whole idea of the celestial spheres, or the crystalline sphere model, where the heavens were perfect and everything about them was perfect, and the circle, or the sphere, happened to be the perfect shape, depending on whether you're dealing with 2 dimensions or 3 dimensions. So they needed to keep everything circular. They also needed to keep the Earth in the center. However, Ptolemy came up with a little bit of a tweak where he put the Earth slightly off-center of each orbit. Or stated, perhaps more correctly, he put the orbits so that they had a center slightly off from the Earth. That way that he could still claim that the Earth was in the center of the universe. These orbits were just slightly askew. They were eccentric. That's the word that we use to describe them. They're eccentric orbits. And then on the other side of the center, an equidistant from the center as the Earth is, he made an equant. And the reason why he did this was because of the varying speed of the planets. And basically that's what all of these things had to do with. The epicycles deal with the forward and backwards motions of the planets compared to the stars, specifically the retrograde motion problem. Putting the Earth off the center of the center of the circle means that you can justify the planet spending more time on one side of the horizon than on the other side of the horizon, because your horizon isn't 180 degrees to the planet in terms of its orbit. And the last bit was using the equant as the point about which there's uniform speed. Not uniform linear speed, but uniform angular speed. So 20 degrees here and 20 degrees here take the same amount of time for the planet to transverse. What that means, though, is that from Earth's perspective, this one's moving pretty slowly in its terms of its linear speed, and over here it's moving quite rapidly. So what you get is a really dramatic increase in the amount of time that the planet spends on this side compared to how long it spends on this side of its orbit. So that's the basic idea behind what Ptolemy was doing. He was trying to account for the strange speeds of the planets, and he used those 3 major methods: the epicycles, the eccentric, putting the orbit off the center of the universe, off of Earth, and using the equant as the uniform speed indicator. Now Ptolemy did this between 100 and 170 AD in Alexandria. He put this all in his book, the Almagest, for the next 1500 years. So until about the 1600s. Some new data rolled in, and the astronomers of the day tweaked Ptolemy's model. And they never needed to make up a new model, and the reason was because Ptolemy's model mostly worked. And when it didn't work, they would just change the size of something. They'd change the size of the epicycles. They'd move the Earth slightly more off-center, as well as the equant, and so on. So there was no data that they couldn't fit the model to. This is, for those who are scientifically inclined, this is kind of the way that science works, but it's also frowned upon. If your model is a good model, then when new data comes in, when you make new observations, your model should have predicted within error where the data lies. And what they were finding in this sort of intervening 1500 years was that it wasn't quite working out that well. There were things shifting. Things were off too far from what the model was predicting. So they would change the model. And in modern science, what we would hope this would do was it would raise alarm bells, and people would say, you know, this isn't quite right. If our model is so far off periodically with its predictions, then there's something we're missing about the model. Maybe our fundamental understanding that led to this model is wrong. But because nobody thought that, nobody was going there, the Almagest really was the greatest. It lasted for 1500 years before there was any challenge to it. And that's actually not even Ptolemy's longest lasting work. He wrote a book called Geography, on geography. And that lasted as the primary text until, I believe, the 1900s. 1800s, 1900s. So it lasted even longer as the primary text. But this process of data coming in, and in this case astronomers, who were not really scientists, they were much more mathematicians than scientists, taking that data and then making small adjustments to the models and to their understanding of what was going on in the universe. These incremental improvements of the existing system is often called normal science. And this is a term that's that's actually introduced by a guy named Thomas Kuhn, who wrote a book called The Nature of Scientific Revolutions. And he claims that normal science is normal science. It's what scientists normally do. And they do it. They work within the same system, within the same model, essentially, until you get to this point where there's an overwhelming amount of evidence to tell you that the model is not right. And we see this happen a lot in science, where we work within the model, we get to about as far as we can go, and then we kind of have to give up and start over. And after 15 years, 1500 years, we finally got to that point. We had Copernicus and his beef. And the problem that Copernicus saw was that, well, you have to understand that in his day and age, there were not things like the internet, the emails, tweets, that sort of thing. So if one astronomer is working on something in Italy, a different astronomer could be working on something in Germany, and they could see the same thing, but they could adjust the model in two different ways to get approximately the same end result. And they didn't communicate with each other. There wasn't even the U.S. Postal Service in places like Italy and Germany at the time. So communication was very poor. And Copernicus saw this, and he realized, all of these different astronomers have these different models due to different tweakings. And over the 1500 years, if your basis is a model that was tweaked by somebody in Germany, you're going to go off in a different direction than somebody who's working off of a model that was tweaked by somebody somewhere else. So you had these very divergent models proclaiming the same thing, saying that they all describe the way that the universe works. And this really bothered Copernicus, because he thought, if there's one universe, which he believed that there was, one Earth, one planet Mars, and so on, then we should really just have one model that does a good job of explaining everything. So he wanted to consolidate the models and make just one. He also felt that the models were too complicated. Hopefully this isn't too hard to believe or understand. I mean, you have all of these different epicycles. You have the equants, you have the deferents. It's very, very confusing and difficult to figure out how that's possible. And all the models were different, and people just kept adding more and more levels of complexity and depth to them. And the one thing that really bothered him, and this is one of the... Well, actually, there's a couple things here. These are actually all very scientific ideas. So you can see the budding of scientific reasoning here with Copernicus. This whole idea of one actual thing happening in the universe. There's one Earth, one Mars, one Sun, one Moon, so on. Meaning that there should only be one model to describe them is a scientific type of idea. We want our model to be a reflection of reality as near as we can make it. So we're not just making up something that's mathematical, which is what most astronomers were doing. They didn't care whether or not their model was right. And with Copernicus, you start to see the buddings of that idea. Like, I really want this model to be the right one, to be very close to what's actually happening in reality. This is another idea that scientists use. There's something called Occam's razor, which basically says the simplest solution wins. And when you're dealing with all these complicated solutions, typically the simplest explanation or the simplest solution is the right one. You don't have to make this Rube Goldberg type of contraption with the planets in order to get a working model. At least that's what Copernicus was thinking. And then this last one was also a big problem for him, and it's one that he really focused on, this inconsistent principles of motion. He felt like if you want to use a circle, you should just use circles. If you say the Earth is the center of the universe, you should make the Earth the center of the universe. If you say that the planet is going around the Earth, then it needs to go around the Earth. And he wanted things to go in uniform circular motion. None of this going at the same angular speed about some point that's off of the center. He felt like it was really, really strange. So he wanted to do what he could to simplify, to consolidate, and to make more uniform in the principles governing it. He didn't want lots of different principles at play.